Dear students, welcome to this next lecture of microcontrollers. So today we will start discussing about how to interface your 8051 microcontrollers with actuators. So in the last video lecture, we were talking about how in an IoT environment you have sensors and actuators, and sensors are the devices that sense some physical quantities like temperature, pressure, humidity, and so on, and then convert those quantities into an electrical signal. And usually those electrical signals are analog in nature, and then you do some sort of signal conditioning, which we also covered in the last class, to convert these electrical signals to an amplified voltage signal. And the voltage signal is also analog in nature, and then you convert those analog signals into digital equivalent, to store them and do further processing on them. And in the last class, we were discussing about how to interface those sensors through analog to digital converter, ADC, to your microcontroller. Okay, and then so that was the sensing part. So this is, let's say if you consider the block diagrams, so this is the sensor, and then you have some form of signal conditioning, and then you have an ADC that will convert these analog signals to your digital signals. So basically these sensors, they are sensing something, let's say temperature or pressure or humidity, etc. And then you have this signal conditioning, then ADC. This goes to your, let's say, the microcontroller. Let's say we are studying 8051 in this module, so let's say an 8051 microcontroller, and then the output of the microcontroller will go to some actuators. Okay, so based on whatever is sensed here, after going through all these steps, the actuator takes some action. Okay, so the purpose of the actuator is to take some action. Now this action can be, let's say, to switch off a heater. Okay, let's imagine that your sensor is sensing a temperature, and if the temperature is too low, then after going through all these steps, this actuator's task is to switch off a heater. Okay, or let's say to move so this is one example. Another example can be to move some stuff. Okay, so there can be many examples of actuation. So basically a robotic arm can, let's say, move something. So based on the inputs from this side, the actuator can be a robotic arm, it can be a switch, it can be a motor. Okay, let's say the motor will turn or rotate, let's say, a robotic arm. Okay, something like that. So in the last class we were discussing about this part. Okay, so we were specifically focusing on the ADC part. Now we will see how to interface with actuators. Okay, so the examples of these actuators can be many, but we will consider especially the motors. Okay, so these rotating type of devices. Okay, so moving on with this background, so let's say the first thing we will study is the DC motor. Okay, So this is the concept of a DC motor, as you can see. So you have probably studied this before in your physics class, that whenever there is a current carrying conductor, like this wire, okay, this wire is carrying some current in this direction, okay. So the direction of the current is like this, and there is a magnetic field applied here. So this is the north pole, this is the south pole, so the direction of the magnetic field is this one. So whenever this arrangement happens, so when an electric current passes through a coil in a magnetic field, there is a magnetic force, okay, and the direction of the force is as shown with these green arrows, okay. So this force is given by this. So this is the magnitude of the current, this is the length of the conductor, and this is the magnitude of the magnetic field, and this force acts perpendicular to both the wire and the magnetic field. So we have this theory that we all have studied previously, okay. So in high school physics, and also maybe in your engineering stage 1 or stage 2, I'm not sure, but I'm very sure that you have gone through this before, and this is a recap of what you have learned before. So the DC motor, when we turn the motor on, okay, so let's say we have a circuit like this. So there is a voltage applied, and there is a resistance here, and then we have this current which is defined, or basically when we turn the motor on, the supply voltage drives a current through the motor, which is given by this, okay. So now the current which is going through this motor, as you saw in the previous slide, the current creates forces that turn the motor, okay. So you will have some magnetic force that will turn the motor, and then the turning motor generates a voltage of its own, and this is called a back EMF, okay. So basically whenever you have this current, the current creates forces that turns the motor, okay, and then the turning motor generates a back EMF. So this back EMF EA tries to oppose this voltage VA, okay. So EA is given by the back EMF is given by this some constant times the magnetic flux density and the rotational speed, okay. So given by this omega m. So basically the current drives the motor because of the interplay between the magnetic and the electric field, and then when the motor is rotating, then because of the rotation of the motor within the magnetic field, okay, so if you go back, so this thing is rotating, right, because of this force. So this force is like this, so it's trying to rotate this coil, okay, and because of this rotation, this coil is actually intercepting this magnetic field because of this rotation, and due to that this back EMF is produced, okay. So basically if you write it in the circuit theory equation form, then this supply voltage is equal to the back EMF plus the voltage drop within this resistor. So when the back EMF now equals the supply, the motor cannot accelerate any further. So now so that's what we have. And now if we multiply both sides by the armature current, okay, so you have this, and this part is the mechanical power, and this is the I square R loss or the power loss to heating of the armature. Okay. So now the power and the torque. Okay, so torque means the rotational force. The power and the torque are related as this. Okay, so basically your back EMF power is equal to this torque times the rotational speed. So therefore the torque is given by this quantity. So basically this quantity EA over omega, we will not derive it here, but this is usually proportional to the magnetic flux density. So you write a constant K times psi, the magnetic flux density. So in that case you get the torque, which is equal to the magnetic flux density times the armature current times a proportional constant. So therefore the torque depends only on the flux and the armature current. So how fast the motor will rotate depends on the magnetic field and the armature current. Okay, so that was the theory of the motor. Okay, so now the concept here is to drive this motor by appropriately interfacing it with your microcontroller. So to do that, there is an interfacing circuit which is called the HBridge. Okay, so the HBridge allows the motor to run in either direction. So if you have a circuit like this with 4 transistors as shown here, so here is the motor, okay, so which is connected to the HBridge like this. So this is a bridge type of structure with 4 transistors which are named Q1, Q2, Q3 and Q4. Okay, so if Q1 and Q4 are connected, so Q1 and Q4 are connected, then basically you have a circuit or a direction of a current like this. Okay, because these two are connected, so these two are behaving like a on switch, so you have a current direction like this. And if Q3 and Q2 are connected, so these two, then you have a current direction in this direction. Okay, so based on this you can turn the motor either in this direction or in this direction. Okay, depending on the current directions, and the current direction depends on which transistors are connected or closed. Or you can also set Q1 and Q3 or Q2 and Q4, okay, for braking. So basically if you do this, then the motor will stop rotating. Okay, and this Q1 and Q4, they cannot be on at the same time. Those are forbidden states, because that will behave as the entire A side to be short circuited, and if let's say similarly Q3 and Q4 are connected, then the entire B side will be short circuited. So there are available ICs that implement this HBridge, or you can build your own circuit like this as shown here. So here are the different states of the HBridge as I just explained. So these are the 2 allowed states where you can have either Q1 and Q4 connected or Q3 and Q2 connected. So these are the allowed states. Okay, I'm sorry, the direction of the current would be like this. Okay, in the previous slides. Okay, so anyway, so these are the 2 allowed states, and this is not allowed, as I said. So it will have a short circuit along this A side, and a very high current will be drawn, and this might burn the circuit. Okay, so here in a schematic form you have the HBridge circuit denoted like this. So you have the motor here, and as if you have 4 switches which are implemented by these transistors. Okay, so S1, S2, S3 and S4. Okay, and then you have the supply voltage here. Okay, so so if these switches, let's say, if I say that, when a switch is closed, that state is 1, and when the switch is open, that state is 0, then you can have a truth table like this based on the configurations of S1, S2, S3 and S4, and based on this you will have different results. So whether your motor moves right or motor moves left, whether the motor brakes or whether the motor coasts. So motor coasts means the motor is rotating at a constant speed. Okay, and then these are the different short circuit states. Okay, so so this is what the HBridge is all about, and this L293 is a sort of HBridge motor driver IC in a 16-pin package. So the L293 and its different pin configurations look like this. Okay, so you can see that you have 4 inputs and 4 outputs possible. Okay, so this is the logic diagram, and you have the set of inputs 1A, 2A, 3A and 4A, and then these are the outputs, and these are the pins representing these outputs, and here are the pins that represent the inputs, and we have also the enable pins. Okay, so there are 2 enable pins, or actually 1 enable pin that can enable both 1 and 2 in, and there are another enable pin which can enable 3 and 4, and based on the input. So let's say if your enable is high and if your input is high, then you have a high output. If your enable is high and input is low, then you have a low output. If your enable is low, then whatever be the input, the output is a high impedance state or a off state. Okay, so based on this you can have a connection like this. So if you have if you're 1A, let's say your enables should be high anyway. If your enable is low, then you have a high impedance state. So let's say your enables are high, and then if your 1A, which is this pin, if this is low and this 2A is high, then the motor will turn right. Okay, so so let's say this is high, so the current direction, and this is low, let's say, so the current direction will be in this direction. Okay, so so the motor will turn right in this direction, and for the other possible combination, the current direction will be opposite and the motor will turn left. Okay, so this is the entire interfacing diagram with your 8051. So this is your 8051 IC, and then this is the L293 IC, and then the motor is connected like this. So pin 3 and 6 are the output of the L293. So these 3 and 6, these are the output across which the motor is connected. So here we have the motor connected to pin 3 and 6, and then your 2 and 7 are the inputs. Okay, so here you can see that your 7, this 7 is an input and 2 is an input. Okay, so 2 goes for 1A and 7 goes for 2A. Okay, so this 2 and 7 are the input. Okay, and then your and then this 4, 5, 12 and 13 are grounded, and 8 and 16 has the supply voltages. Okay, so this is the usual microcontroller, which where you have this um, clock input through these two crystals, and then you have a switch here. Okay, so the switch will actually either power on this microcontroller board or power off. Okay, so so with this arrangement you can have a bidirectional DC motor with this arrangement. Okay, so port 1.0 goes to the one input of L293, and port 1.1 goes to the another input. Okay, so you can write a code like this to control the motor assembly. Okay, so let's say you can move this binary combination to port 1. So basically your port 1.1 will be activated in this case, and if you move this combination, then port 1.0 will be activated, and you can use a delay, okay, in between. So basically whenever your port 1.0 is activated with this arrangement, then you have input to this pin 2 of L293. So this will be 1, this will be 0, let's say, and then you will have a current passing through the motor that will turn the motor in clockwise direction. When you have when you have this arrangement in the port 1, then your motor will run anti-clockwise. Okay, and then you can use a delay also. Okay, and this delay subroutine can be written like this. So you can have a 1 second delay or or anything, any n second delay, or whatever your application requires. Okay, so this is a very simple arrangement. So once you have this circuit ready, all you need to do is to activate port 1.0 or port 1.1 with a delay. Okay, so that's what this code is all about. So you are moving a binary configuration to this port so that port 1.1 or 1.0 is activated, and then you can turn the motor in a specific direction. So so you can also have a little more sophisticated arrangement, like a bidirectional motor with a push button control. So in such a case, like, you can use the port 3 of the microcontroller for some input switches. Okay, so 3.0 and 3.1 in particular. So in this case, when you press this switch S2, then this this will act as a switch. Okay, so basically so when you have this P3, okay, which is all 0, okay, so this initiates P3 as the push button interface. Okay, and then you clear your P1, okay, so that the motor is off initially, and then you move the current state of P3 to the accumulator. Okay, and then you compare it with this this binary arrangement. Okay, so if this switch is closed, okay, then you will have 3.0 as a high voltage state. Okay, so 3.0 will be your 1, logic 1, when this S2 is closed. Okay, and if 3.0 is logic 1, then your port 3 will look like this. So 0 0 0 0 0 0 0 1. When your S3 is pressed, then 3.1 will have a high voltage here, and in that case, so this is for S2, okay, and this is for S3. So in this case, the logic configuration of port 1 will be this. Okay, so this is 3.1. okay, so now what you want to do is that you just move these configurations whatever it is based on S2 is closed or S3 is closed. You move these configurations to the accumulator and then compare it with either this number. Okay, so if this is the number, okay, which means S3 was pressed. Okay, so if this is the number, then you jump to level 1, and level 1 is basically if this is not equal to, so CJNE means compare and jump if not equal. So if whatever is in your accumulator is not equal to this number, then you jump to level 1 and then you compare it with this number. So it has to be either this number or this number. So if it is not equal to this number, then you jump to level 1 and then compare here. And then if it is not equal to both these numbers, then you go to level 2, which is telling you to go back to this line. Okay, and then check again. Okay, now if they are equal, so if not equal, they will go to level 1 and level 2. If they are equal, let's say if this accumulator contents is equal to this number, then it moves to the next line. Okay, and in the next line, what it does is to move this number to P1, and if that is the case, then this input 2 is activated and then the motor rotates in this direction. And then if if the otherwise happens, so when you are comparing with this number and if it is equal, then it will go to the next line and it will move this number to P1, which means the previous case was this would have been activated for so for this number, for this number, your input 2 is activated, and for this number your input 7 is activated. Okay, so I hope you got the concept. So basically, based on the switch configurations, you are moving a binary configuration to port 1 so that either this pin is activated of the L293 or this pin is activated, and the motor will either rotate in this direction or this direction. So based on this push button configuration, you are implementing a bi-directional motor. Okay, so that was the DC motor. So that was like as simple as that. So now we will move on to the stepper motors. Okay, so these are electric motors without the commutators. Okay, so basically, if you see the structure of the DC motor here, so you have a conductor here. So this is called the commutator. So this was the current carrying conductor, and then the magnet was fixed. Okay, so in stepper motor you have the opposite arrangement. Okay, your magnet will be in the middle. Okay, and that will be rotating, and we will have the current carrying conductors in the sides. Okay, so I will just get back to the stepper motor and show you the structure. Okay, so typically all windings in the motor are part of the stator. Okay, so stator means the one that is stationary. Okay, so the stationary part is called stator, and rotor is the rotating part. Okay, so all the windings or all the current carrying wires, they are part of the stator, and the rotor or the rotating part is a permanent magnet. Okay, so unlike DC motors which spin round freely when power is applied, stepper motors require power pulsed in specific patterns. So this is more of a digital in nature, as the name suggests. So it rotates in steps. Okay, whereas DC motor is more of an analog in nature, where it spins around freely. Okay, So each pulse is designed to make the motor rotate one step. Okay, and this is highly accurate, and these are commonly used in many applications, for example the computer disk drives, printers, etc. Okay, so so this is there is another motor called servo motors. So servo motors require analog feedback control. For example, potentiometer measures the rotor position and the current is driven through the motor, which is inversely proportional to the difference between the desired and current positions. So for some applications there is a choice between using these servo motors or stepper motors, and they have very subtle or very little differences. um, so for example, servos offer better control over the torque. Steppers provide high torque without high voltages, whereas steppers are steady when at standstill, but the servos oscillate. Okay, so the steppers, the stepper motors, there can be two types. Okay, unipolar and bipolar. So here, first of all, you notice that this rotor, this is a permanent magnet with south pole and north pole. Okay, and this is the one that rotates. Okay, and then you have this windings, and if you apply current to these windings, then there will be magnetic field across these points, and this will enable an interplay between the magnetic field of this rotor and this induced electromagnetism, and that will create the force for this rotation. Okay, so that there could be a unipolar motor. So this is an example of an unipolar motor. Okay, so they usually have four coils, as you can see. Okay, so this is one, this is another one, here also we have one, and then this is another one. So there are four coils which are switched on and off in a particular sequence. So based on this directionality of the current across these coils, let's say if you have a current here and no current here, and then current here and no current here, then you can imagine that this is one particular sequence. Then you can have several combinations of this four coils, whether it has current or it doesn't have current. Okay, and then your rotor rotates accordingly. Whereas in bipolar motors you have only two coils, so this is one and this is another one. Okay, and here the directionality of the current is reversed. Okay, in a similar sequence. So either if you have, so here you can have four states. Okay, for the four different coils. Here you have two coils, but then depending on the directionality, each coil would have two separate states. So here also you can have four states in this case also. So this is the difference. So you have unipolar and bipolar stepper motors. Okay, so I'll show you a video on unipolar and bipolar stepper motors, and I will come back after the video.
Now that we have seen some of the types of stepper motors available, let's take a look at sub-variations of both the permanent magnet and hybrid motor types. These two subcategories are determined by how the leads from each phase winding is brought outside of the motor. The first example is a bipolar configuration. Here you can see that each winding lead is brought out separately. This type of winding, depending on the voltage applied and to which lead, can produce current flow in two directions. This allows each stator pole to be magnetized to either north or south. The unipolar configuration, on the other hand, only allows current flow in half of the winding at one time. Notice that each winding has a center tap that is brought outside of the motor along with each winding lead. Let's take a closer look at how the unipolar type of motor works. The center tap lead is connected to a positive voltage source in this example. Driving one of the leads on winding A to ground allows current to flow in one half of the winding generating a polarity on the stator poles, and the rotor rotates accordingly. Next, the grounding source is removed from the winding A lead, and one of the winding B leads is driven to ground. Again, current flows in half the winding, and the appropriate stator poles are energized. This continues to rotate the motor 360 degrees. On the other hand, bipolar motors allow current flow in both directions through each winding. Applying a voltage to lead A' and grounding lead A generates current flow, resulting in the stator polarity shown above. Removing the voltage from winding A and applying a positive voltage to lead B' on winding B, while driving lead B to ground, generates current flow and stator polarities as shown above. This continues to rotate the rotor 360 degrees. Let's compare both winding configurations. Unipolar motors only allow current flow in half the winding, while bipolar offers bidirectional current flow. Since torque is related to winding current, bipolar motors will generate greater torque than unipolar motors. Furthermore, due to the fact that unipolar windings are thinner than bipolar motor windings, more wire is needed, thereby increasing the winding's resistance. This could cause increased power loss via the winding potentially raising the temperature considerably. However, using a bipolar motor will require more complex circuitry, potentially increasing the cost of your design and use up more of your board's real estate. One other point to make here: since unipolar motors do have both ends of the windings being brought out of the motor, we could connect them in a bipolar configuration by simply omitting the center tapped lead.
Okay, so welcome back after that video. So going back to the discussion on stepper motors, so you can see that you have you have this armature, which is the rotating part, and usually this armature is magnetized. Okay, and these are the different coils. Okay, or the stators. Okay, so there usually these will have, as you can see here, these stators are actually holding some wires, okay, that are coiled around these stators. So usually these stators will have wires like this. Okay, so there will be some wires that will be coiled around this, and then there will be some electric current flowing through these coils, of course, and depending on the electric field's directionality, okay, you will have this armature rotating in a particular way. So basically, by turning on the field coils, these coils, okay, in the correct sequence, the armature can be made to follow the field. Okay, so these are numbered or labeled like A, B, C, D, and again the exact 180 degree opposite is again numbered or labeled the same, which is A, then B, C, and D again. Okay, so based on the sequence on how these different different stators are activated, let's say, or a current is applied, the armature will rotate accordingly. So let's say you have A and B together. Okay, so let's say this is your step 0 and your rotor is at this position. Okay, as shown here. Okay, so let's say in step 1 you are jointly activating A and B. So that means you have current in these A coils and these B coils, so which you can state as a 1 1 0 0 position. So A, B, C, D, according to the fact that whether you have current or no current, you can say these as binary 1 and 0. So A, B activated together means this is a 1 1 0 0 sequence, and in that case the rotor will be in between these two stators, okay, trying to follow this field, okay. And then when you have a current in BC, which is, let's say, 0 1 1 0, then the rotor moves in this direction and follows this configuration. Similarly, when you have current in CD, then you have this particular configuration of the rotor. So in that way, you can see you can move this rotor in steps, and different step is denoted by these different combinations of these stators that has current in it, okay. So based on this digital sequences, you can program your microcontroller, and you can interface your stepper motors, okay, in a way that when you try to put some binary combinations, let's say, into your output ports which are connecting these stepper motors, the stepper motor will have this particular steps, okay. So let's say this is how stepper motor is connected to a 8051. So as you can see, all these are common, all these connectivities. So far you have known about these parts. Just focus on this part, okay. So this port 1.0 to 1.3 in particular are connected to this 1 2 3 4 inputs of this particular IC, which is called ULN 2003. So this is basically interfacing this stepper motor with the microcontroller, okay. And this is a bipolar stepper motor, okay. And based on the outputs here, there will be the directionality of the current will be in this way or this way, and on this way or this way, right. So therefore you can see that by placing some binary combinations in these 4 pins of port 1, you can rotate this stepper motor through different steps and precisely along these steps. So if you have 1 1 0 0, let's say, in these 4 pins, then you can have a certain orientation of the rotor, and so on. So you can have, so this is the ULN IC, by the way. This is the ULN 2003 IC pinout diagram, okay. So you can program like this. You can have a full step sequence, as you saw a couple of slides back, and you can write a program like this, okay, where basically you are moving in your port 1 some numbers and calling delay in between, okay, and then you are repeating this thing again. So based on these numbers, it will be going through these steps, okay. So first you have step 1 1 1 0 0, for step 2 you have 0 1 1 0, for step 3 you have 0 0 1 1, and so on, okay. So that was a full step sequence. You can also have half step sequences as well, okay. So basically you have this step, okay, let's say this is your initial step, okay. Then if you just activate A, so earlier if you see, you are activating 2 stators together always. So here AB, here PC, and so on. So this is a full step sequence. You can have half step sequences, like this is the initial step where 2 stators are activated, but then you can have only in the next step only stator A. So the armature will be aligned across this axis, okay. and then you can have AB, so it will be in between A and B, and then you can have only B, you can have BC, then only C, and so on. So you can have 8 steps instead of 4, and this is called an half step sequence. So you can have step 1 as A, step 2 as AB, then B, BC, C, CD, and so on. And these are the binary combinations that you need to put to configure these steps. Okay. So this scenario has 25% lower torque, since half the time only one field coil is holding the armature in position. So the resolution is doubled as well. Okay. So in motors with many poles, the step sequence could be at to any one of a number locations in a full rotation. Okay. So this is what I wanted to mean. So this one has 4 phases, okay, and it has 8 poles. Okay, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, 8 poles and 4 phases. Okay, and therefore it can have 32 steps per revolution if you have full step, and if you have half step you can have 64 steps per revolution. So this approach is not used very often to create a large number of steps per revolution, as it would lead to a very intricate structure. Okay, so this is a very intricate and complicated structure, as you can already see. So lots of windings on very small formers. Okay, so this is not often used. What is used is like something like this. Okay, so you can have, let's say, X stator poles and Y rotor poles, and let's say Z is the degree rotation per step. So you have an equation like this. Okay, so basically if you have X equal to 4, so if you have 4 stator poles and 3 rotor poles like this, then you can have Z equal to 30 degree according to this equation. So in that case you can have 12 steps per revolution. So this was giving you 32 steps per revolution, but for this you need to have so many phases, so many poles, and this becomes a very intricate structure. But let's say with only 4 and 3 you can have 12 steps. So you can also have 32 steps. So let's say or more, let's say 360 by 32, whatever it is, and then you can have this ceiling. So that will give you about how much? About 12 degrees. Okay, so you can have this equation 360 degree by X minus 360 degree by Y equal to 12 degrees. Okay, and then you can find out X and Y that that satisfies this, and you can say, let's say, so let's say if your X is 15, let's say, or X is 20, then this will be 18, and if your Y is, let's say, so let's say if your X is 20, okay, and your Y is 60, okay, or maybe this is too much. Okay, let's say so let's say if your X is, let's say this can be done as, this 12 degree can be done as, let's say, 24 degree minus 12 degree. Okay, so to get 24 degree out of this 360 by X, what you want to do is that your X can be 15. Okay, and to get 12 out of this, your y can be 20, or no, 30. Okay, so by having x equal to 15 and y equal to 30, let's say, you can have this 12 degree z. Okay, so if you have 12 degree of z, you can still have 32 steps per revolution. So my point is that by having let's say less number of rotors, rotor poles and stators, you can still have 32 rotation instead of having, let's say, this complicated structure. Okay, so this is what is practically used, this type of structure. Okay, so if the number of poles on the armature differs from the number of poles produced by the field windings, then a vernier effect occurs that can lead to a large number of steps per revolution. The rotor only rotates through an angle equal to the difference between the rotor and stator angular separation. Okay, so for the 4 pole and 3 pole scenario, where you can have 12 steps per revolution, so the rotor will move at each step through an angle of 30 degree like this. So if your A is activated, this field, then let's say this is your initial position. Then if your B is activated, it moves 30 degree towards this direction, and then if your C is activated, it again moves 30 degree, and then if your D is activated, it moves 30 degree, and so on. So it moves in increments of 30 degree or steps of 30 degree, and you can have 12 such steps, 1, 2, 3, 30 degrees. Okay, so let's do a summary then. So you can have half step or full step, or you can also have micro steps like this. And although the physical construction of a stepper motor can vary, the drive sequence for all are the same or very similar. So the designer has the choice of producing the sequence using software or using a dedicated chip. Okay, so these dedicated chips take 2 control inputs, one defining direction and the other a clock pulse, to advance the motor to the next position. Okay, so we will do some practical examples later on in some tutorial, and you will learn more about different applications of these stepper motors. Until then, this is what I have today, so I will end this video lecture and I will see you in the next video lecture. Thank you.